I was playing around with one of those high-end image generators last night. I typed in this incredibly specific prompt, something like, cyberpunk raccoon fixing a toaster in a neon alleyway, and then I just sat there. I watched the little progress bar just creeping forward, 10%, 30%. It felt like I was back in the dial-up era waiting for a JPEG to load.
A classic sampling bottleneck. It's the bane of modern generative AI. We have these models that can literally imagine anything, but they need to think about it for a long time before they show you the result.
Exactly. And in tech time, 10 seconds is basically an eternity. But here's the thing that always bugs me. Why do we have to wait? Why does the AI need to take 50 or 100 little steps to draw the raccoon? Why can't it just draw the raccoon?
That is the billion-dollar question. And frankly, until, very recently, the answer was simply because the math says so. But that's changing.
Which brings us to today's deep dive. We are looking at a paper that I think is going to be a landmark. It's titled MeanFlow. MeanFlows for one-step generative modeling. It's coming out of a collaboration between CMU and MIT, featuring some heavy hitters like Zhengyang, Geng, Zico, Kolter, and Kaiming.
Absolute titans in the field.
Yeah.
When names like that are on a paper, you pay attention.
And their claim is pretty audacious. They say they've cracked the code to generate high-fidelity, photorealistic images in a single step. One function evaluation, boom, done. And they're doing it without the usual tricks. No massive teacher models, no complex distillation pipelines, just pure reimagined calculus.
It really is a fundamental shift. It changes the physics of how we think about generation.
Yeah.
Instead of simulating a journey step by step, they're calculating a teleportation.
So if you are listening to this and you're tired of the loading bar life, or if you're a developer trying to cut your inference costs by like 90%, stick around. We are going to break down how MeanFlow turns a curved road into a straight line.
Let's do it.
To appreciate the solution, though, we have to really understand the problem. Why are current models, like Stable Diffusion or the new Flux models, so slow? What are they actually doing during those 50 steps?
To understand that, you have to visualize what these models are doing mathematically. They're solving a differential equation. Think of it this way. The model starts with random noise. That's point A.
Okay.
Once you get to a clear, crisp image, that's point B. But the space between them isn't empty. It's a complex, high-dimensional vector field.
Right, vector field. I always visualize that as like a map full of little arrows pointing where to go.
Exactly. In standard flow matching or diffusion, the model learns the instantaneous velocity. It looks at the noise and says, right now, at this millisecond, I need to move in this direction at this speed to get closer to an image.
But it only knows the direction for right now. It doesn't know the whole path.
Precisely. It's like driving in a dense fog with headlights that only show 5 feet ahead. You see the road curving left, so you turn left.
Yeah.
You move forward 5 feet. Now you see the road curves right, so you adjust.
You have to constantly check your position and adjust your steering.
Constantly.
And because the path from noise to data is usually curved, it's nonlinear, you can't just floor it. If you tried to drive in a straight line from the start based only on that first glance, you'd, drive off a cliff?
Right. If you just took that initial velocity and multiplied it by the total time, you would end up in a ditch. You wouldn't get a coherent image. You'd get a blurry mess. That's why we have to take small steps. Step 1, adjust. Step 2, adjust. Step 50, finally arrive.
So the steps we wait for are the model rechecking the map and correcting its course. It's essentially integrating the path by taking tiny baby steps.
That is numerical integration. It's accurate, but it's incredibly inefficient. That is the sampling bottleneck.
Okay, so that's the status quo. Enter MeanFlow. How do they fix this without just making the computer faster?
They change what the model learns. Instead of learning the instantaneous velocity, what direction to move right now, they want the model to learn the average velocity.
Average velocity. I'm having a high school physics flashback.
Mm-hmm.
Displacement over time, right?
Correct. Let's go back to our car analogy. You are at the point A, the noise. You want to get to point B, the image. The road might be winding and curved, but the average velocity is just a straight line vector pointing directly from A to B.
So if I knew that specific vector right at the start,
you wouldn't need to steer. You wouldn't need to check the map 50 times. You would just take that vector, multiply it by the total time, and jump.
One single step.
One single step. You essentially tunnel through the curved space directly to the destination.
That sounds fantastic, but I feel like there is a massive paradox here. To know the average velocity, the straight line to the destination, don't you need to know where the destination is?
You have hit the nail on the head. That is the catch.
Because the destination is the image, we haven't generated it yet, so we're trying to learn a shortcut to a place we've never been.
Exactly. Usually, to find the true average velocity, you would have to run that slow 50-step integration process to simulate the whole curve path, see where you end up, calculate the average, and then teach the model that.
But doing that for every single training image would take forever.
It becomes computationally intractable. It's just too expensive.
So this is where I get skeptical. How do they get around it? Are they just guessing?
No, and this is the brilliance of the paper. They derive something they call the MeanFlow identity. This is the core contribution. It's a mathematical derivation that links the two concepts. They found a way to calculate the average velocity using only the instantaneous velocity without needing to simulate the whole path.
Okay, walk us through that. How do you get the macro, the full trip from the current moment?
It involves a bit of calculus, but let's keep it conceptual. The equation basically says the average velocity, let's call it $, is equal to the instantaneous velocity, let's call it $, minus a specific correction term.
A correction term, what is it correcting for?
It corrects for how the average itself is changing over time. The term involves the time remaining, multiplied by the derivative of the average velocity.
Okay, translate that into English for me.
Think of it like this. The model looks at the current location. It sees the instantaneous velocity, the local traffic flow. Then it uses this MeanFlow identity to estimate, okay, the traffic is moving this way right now, but based on the rate at which the flow is changing, the overall trip average must be that way.
So it uses the local curvature to predict the global straight line.
Exactly. It creates a target for the neural network to aim at. The network learns to predict this straight line vector directly from the noise.
But wait, you mentioned a derivative term, the derivative of the average velocity. In my experience with machine learning, calculating derivatives of complex functions usually means expensive computation. If we have to calculate how the output changes with respect to time, aren't we just trading one bottleneck for another?
That is exactly the skepticism you should have. Calculating derivatives can be a nightmare. But this is where the modern deep learning stack comes in to save the day. They compute this term using something called a Jacobian vector product, or JVP.
JVP. I see that in the PyTorch documentation and usually scroll right past it because it sounds terrifying. What is it actually doing?
It sounds scary, but it's actually very efficient. In simple terms, the Jacobian matrix represents how every output of the network changes with respect to every input. It's a massive grid of numbers. You never want to calculate the whole thing.
Right. For an image with thousands of pixels, that matrix would be billions of numbers.
Exactly. But here we don't need the whole matrix. We only need to know how the output changes with respect to one thing, time. We just need the product of that matrix and a specific vector. JVP allows us to compute just that product in a single pass.
So instead of mapping the whole terrain, we just check the slope directly under our feet in the direction of time.
That's a great analogy. And because of how libraries like JX or PyTorch are built, this costs roughly the same as one extra backward pass.
So how much does that add to the training time?
The paper says the overhead is less than 20%. So training this MeanFlow model is only marginally more expensive than training a standard diffusion model.
That's negligible in the grand scheme of things, especially if it saves you 99% of the time when you actually use the model.
Exactly. And there's one more technical trick they use to keep it stable. They use a stop gradient on the target.
Stop gradient. That's basically telling the AI, don't try to change the target itself, just try to hit it, right?
Yes. Without it, the model would get into a feedback loop where it tries to adjust the math of the target to make it easier to hit rather than actually learning the flow. It's like a dog chasing its tail. The stop gradient anchors the target so the learning is stable.
So we have a model that learns to shoot straight from noise to image. It uses this MeanFlow identity to figure out the path and JVP to calculate it efficiently. But let's talk results. Does it actually work? Because I've seen one-step models before, and frankly, the images usually look, well, a little melty.
Or they have that weird blurry texture. That's usually the result of distillation.
Right. Let's distinguish that. Most fast models today, like consistency models or the turbo models, are distilled, aren't they?
Yes. Usually you train a huge, slow, smart teacher model first. Then you train a smaller, faster student model to try and copy the teacher's homework. It works, but it's lossy. You lose detail, and it's a complex pipeline to manage.
And MeanFlow.
MeanFlow's trained from scratch. No teacher, no pre-training. It learns the one-step generation directly from the data.
That sounds cleaner. But what do the numbers say? I want the scoreboard.
The standard benchmark is ImageNet 256 by 256. The metric is FID for shed inception distance. For those who don't know, lower is better. 0 would be a perfect match to real data.
Okay, set the stage. What were the previous one-step models getting?
A prominent one-step model called Shortcut was clocking in at an FID of around 10.6.
10.6. Okay.
Another method called IM iterative matching with momentum was around 7.7.
And MeanFlow?
MeanFlow hits 3.43.
Whoa. 3.43 versus 10.6. That is a massive drop. That's not an incremental improvement. That's a completely different league.
It is. It puts it in the same ballpark as the slow multi-step models. It essentially closes the gap. You're getting the quality of a 50-step diffusion model in a single step 1 NFE.
One NFE. One number of function evaluations.
Just one call to the network.
I was looking at the sample images in the paper, figures 1 and 5 specifically. There's a snowy mountain range here. The clouds are distinct. The peaks are sharp. There's a chameleon where you can actually see the individual texture of the scales. It doesn't look averaged in the sense of being blurry.
That's the beauty of the math. Average velocity doesn't mean average image. It means the optimal vector to get to the sharp image. It lands you right on the manifold, the specific slice of mathematical space where real, crisp images exist.
Now, there is a practical elephant in the room that we have to address. Guidance.
Ah, yes, CFG.
Classifier-free guidance. This is the secret sauce that makes Midjourney and Daily look so good. It forces the model to listen to your prompt, make it look more like a cat. But usually that comes with a tax, doesn't it?
A heavy tax. Traditionally, CFG requires running the model twice for every single step. Once conditioned on the prompt and once unconditionally just noise. Then you mathematically combine them to push the image toward the prompt.
So if I have a one-step model, but I have to run it twice for CFG.
You've just built a two-step model. You've doubled your compute cost and halved your speed.
Exactly. It defeats the purpose of the whole single-step breakthrough. How does MeanFlow handle this?
They pull off a bit of a magic trick here. They treat the guidance not as a sampling hack that you do at the end, but as a property of the ground truth itself.
A property of the ground truth. What does that mean?
They define a guided average velocity. They say, the vector we want to learn isn't just the natural flow. It's the flow that has already been boosted by the guidance scale.
So they bake the guidance into the training target.
Precisely. During training, they randomly drop the class label sometimes, standard practice, so the model learns both conditional and unconditional flows. But then, via the MeanFlow identity, they derive a target that represents the fully guided trajectory.
So at inference time, when I'm sitting at my computer and I type astronaut riding a horse,
you run the model exactly once. The network predicts the vector that already includes the guidance push. You get the high adherence to the prompt, the high contrast, the sharp details, all for the price of one NFE.
That is significant. It's a free lunch in a field where free lunches are rare. Usually quality costs compute. Here, you get the quality boost of guidance without paying the inference tax.
And the data backs it up. If you look at their scaling charts, as they ramp up the guidance scale, the FID improves dramatically. Images look better, but the cost stays perfectly flat. They even introduced a mixing scale during training to make sure the model balances the prompt and the noise perfectly.
This seems to solve the complexity issue of things like consistency models. I remember reading about those. They require curriculum learning, where you slowly change the rules during training. It sounded like a nightmare to tune.
Consistency models are brilliant work, don't get me wrong. But yes, they rely on a heuristic constraint. The output at time t should look like the output at time t minus epsilon. MeanFlow is different because it's derived from the definition of velocity itself. It feels more robust. It's more physical.
Speaking of physical, the authors actually make a really interesting comparison in the conclusion. They talk about physics simulations.
Yes, this caught my eye too. They compare it to multi-scale simulations.
Break that down for us. Why are AI researchers talking about physics?
Well, generative AI and physics share a lot of math. In physics, say you're modeling a river, you have the microscopic turbulence, water molecules crashing into each other, swirling around. That's the instantaneous velocity. It's chaotic and curved. But you also have the macroscopic flow, the river moving downstream. That's the average velocity.
And usually, to know where the river goes, you have to simulate the molecules.
Right, if you want to be precise.
Yeah.
But MeanFlow suggests a way to link them. It says, if we understand the local turbulence, the derivative, we can predict the macroscopic flow. That's a way of coarsening the simulation, skipping the tiny details to get the big picture correct.
That sounds like a concept that could go way beyond just generating static images.
I think that's the most exciting part. If you can compress a complex generation process into a single step by modeling the average flow, what else can you apply this to?
Well, look at text. Large language models. We all know how they work. Token by token. The cat on the dot mat. It's iterative. It's slow.
Could you model the average semantic velocity of a paragraph?
Hmm.
Could you jump from a question directly to the answer in one continuous flow step?
Instant reasoning. No thinking time. No token churn.
It's speculative, of course. Text is discrete words are distinct units, unlike pixels, which are continuous. So the math isn't a one-to-one transfer. But the principle of modeling the destination rather than the journey, that's powerful.
Or video generation. Video is famously hard because it takes so much compute.
Exactly. Video is just a volume of data time, height, width. Instead of generating frame 1, then frame 2, then frame 3, could you predict the flow of the entire scene and generate the whole video block in one shot?
The dimensionality of that makes my head hurt, but if MeanFlow scales.
And the scaling plots in Figure 4 suggest it does. As they moved from their base model to the XL model, performance kept getting better. It hasn't hit a ceiling yet.
So let's wrap this up for the listener. We've moved from a world where AI has to painstakingly crawl along a curved path, constantly checking its map, to a world where AI can calculate a straight-line shortcut through the noise.
A shortcut that is mathematically derived, stable to train, and supports guidance for free. It's a very elegant solution.
It turns the sampling bottleneck into a sampling highway.
And it does it with elegance. It's not brute force, it's better calculus. That is what I love about it.
So the next time you're using a generative tool, whether it's for art, code, or eventually video, and it feels instant, you might just have MeanFlow to thank.
Or whatever comes next, standing on its shoulders.
Exactly. Big thanks to the researchers at CMU and MIT for this fascinating work. It's a dense paper, but the implications are huge. And thanks to you for listening.
Always fun to dig into the math behind the magic.
Here is a thought to leave you with. If we can mathematically calculate the average of a creative process to skip the work, does that change the nature of the creativity? Or is it just efficient delivery? Something to chew on. We'll see you in the next deep dive.